Welcome back. Let's learn about smooth intervals of space curves. Alright, so another use of the derivative for vector-valued functions is the ability to determine smoothness of a plane curve or space curve. And what it means for a curve to be smooth is that the curve does not have any sharp corners or points. So all the curves on the screen right now are examples of curves that are completely smooth. They don't feature any sharp corners or points or anything that would break the smoothness of the curve. And of course, that would include any type of asymptote that you may encounter as well. None of these curves feature anything that would make them not smooth. And so you can see that here with these three curves. For this one, we have a plane curve that just spirals out from the origin. The entire curve is smooth. Same thing with this space curve here. If you follow the curve, you'll notice that there are no sharp corners or points. Now, you could argue that where it starts is a point, but if we're assuming that this curve goes on forever in both directions, then of course it is completely smooth and it has no sharp corners or points. And then finally, with this space curve, you can sort of see we have these waves that are making their way around the z-axis. This also has no sharp corners or points. It does have a lot of curves, it goes up and down a lot, but none of those curves are sharp. There are no corners or any areas where the curve comes to a point. Okay, so I hope these curves make it very clear what it means for a curve to be smooth. And so what we're going to be interested in doing for plane curves and space curves is determining the intervals for which a curve is smooth. Because unlike these curves on your screen right now, not all plane curves and space curves are completely smooth. Some of them will have sharp corners, some of them will have points, or maybe an asymptote or something that breaks up the curve and prevents it from being completely smooth. And so in order to determine the smoothness of a plane curve or space curve, we have to know what makes these curves not smooth. What would make a point on these curves not smooth? Well, as it turns out, a plane curve or a space curve, but ultimately a vector function is smooth on an interval as long as its derivative is not zero or undefined. Or in other words, the derivative of a vector function cannot be the zero vector. All right, so more formally, here's the definition. A vector function r of t, which has three components of f of t, g of t, and h of t, is smooth on an open interval I. We're just calling the interval I, that's all that means. The vector function will be smooth on that interval when the derivative of those three components are continuous on that interval and the derivative of the entire vector function does not equal the zero vector. All right, in other words, all three of these derivatives, f prime of t, g prime of t, and h prime of t, cannot all equal zero for any value of t on I. All right, and so it's important to realize here that all three of those components of the derivative of the vector function must equal zero for the same value of t in order for the curve to not be smooth at a point. Okay, so it's not enough if just f prime of t equals 0, or if just g prime of t equals 0 for a specific value of t. All three of these derivatives of the components of the vector function must be equal to 0 at the same value of t in order for that value of t to be a point where the vector function or the curve is not smooth. Okay, and so as you can imagine, the way that we would determine where we have smooth intervals is to find any values of t or any points where the curve would not be smooth, meaning where the derivative of the vector function is equal to 0, or where that derivative might be undefined. And we just exclude those values of t from our smooth interval or smooth intervals, depending on how many points we find where the curve is not smooth. All right, and we call those points where the derivative of the vector function is equal to the zero vector, we call those cusps or nodes. Those are the points where a curve is not smooth. I will most likely call them nodes as opposed to cusps, but both of those terms would be accurate when describing points where a plane curve or space curve is not smooth. Okay, now if we look at an example here we have a plane curve represented by this vector function. R of t is equal to a vector with an x component of 5 cosine t minus cosine of 5t, and a y component of 5 sine t minus sine of 5t. And we're just looking at the values of t from 0 to 2 pi, which forms this entire shape. Okay, and so based on what we've talked about so far in this video, maybe you can already look at the graph of this plane curve and see the intervals where the curve is smooth. You might even be able to point out the nodes or the points where the curve is not smooth. In particular, I'm referring to these 4 points that I have labeled here: t equals 0, t equals pi divided by 2, t equals pi, and t equals 3 pi divided by 2. All 4 of those points are points on this curve where we come to a sharp point, all right? Or you could think of it as a sharp corner. Everywhere else, this curve is smooth, right? This is a smooth section, but then you come to a sharp point, then you have another smooth section, but then you come to another sharp point, then you have another smooth section that comes to a sharp point, and then you have one more smooth section before coming back to that same sharp point that we started at. All right, so just looking at this curve visually, we can see that there are 4 different smooth intervals for this plane curve. They are from t equals 0 to t equals pi divided by 2, from t equals pi divided by 2 to t equals pi, from t equals pi to t equals 3 pi divided by 2, and from t equals 3 pi divided by 2 to 2 pi, right? These are the 4 intervals for this plane curve where the curve is smooth. We're including all values of t for the vector function except the values of t where we have those nodes, where the curve is clearly not smooth because there is a sharp point. All right, that's why we have all these open brackets around these endpoints, because we're not including those values of 0, pi divided by 2, pi, 3 pi divided by 2, and 2 pi in the smooth intervals. Those are values of t for which the curve is not smooth. And furthermore, those would also be the values of t for which this vector function's derivative would equal the 0 vector. All right, I didn't go through the math here because we're going to be doing that in the rest of our examples in this video, but if you took the derivative of this vector function, you would find that these are the 4 values of t for which both components of the derivative equal 0, and so therefore that would be where the curve is not smooth. And so those are the values of t that help us create our smooth intervals that describe where the curve is smooth and where it's not smooth. Okay, and one more important thing to note about smoothness in general is that if a curve is smooth at a value of t, then that guarantees that that value of t would have a tangent vector. All right, we spent the last lesson talking all about tangent vectors, how to find a vector tangent to a point on a curve, whether that's a plane curve or a space curve. And what we didn't really talk about is that those tangent vectors only exist at a value of t if the curve is smooth at that value of t, okay? Because as you can see with this specific curve, the points where the curve is not smooth couldn't have a tangent vector, right? It doesn't make sense. How do you describe the direction at these sharp points? Well, we don't know, right? It's just like when you had a point where a function wasn't differentiable in Calculus 1. That typically happened where you had sharp corners or points on a function. The same idea applies here. And if you think about it even further, it does make sense because these nodes, or the points where the curve is not smooth, those are where the derivative of the vector function equals 0, right? Which means it's just the 0 vector. And so that means that the tangent vector is just the 0 vector, but that doesn't really make any sense because the 0 vector is just a point, right? The 0 vector doesn't really give you any direction. It's just a point. All right, so that's something else that you just want to keep in mind. If a curve is smooth at a value of t, that guarantees that a tangent vector exists at that point. Okay, but with that, that is everything you need to know conceptually about the smoothness of plane curves and space curves. But now let's actually take a look at some examples where we do the calculations to find intervals of smoothness for vector functions. And so here's our first example. We want to find the open intervals on which the curve represented by the vector function is smooth. And our vector function is r of t is equal to t squared times I plus t cubed times j. All right, so we just have a very simple two-dimensional vector function here. We're working with a plane curve, and our goal is to determine where this vector function is smooth or not smooth. All right, and so what we're going to do is take the derivative of this vector function, and then we're going to look for 2 things. We're going to look for any values of t for which the derivative might be undefined, because that's where it would not be continuous. and so therefore the curve would not be smooth. But then we also want to check to see if there are any values of t for which both of the derivative's components are equal to 0. Okay, so let's start by taking the derivative of this vector function. We'll have r prime of t is equal to 2t times I plus 3t squared times j. All right, we just used the power rule for derivatives on those two components. Now, looking at the two components of our derivative here, are they defined for all values of t? Are there any values of t that would make this vector function undefined? And the answer is no. There is no value of t for which this vector is not defined. You can plug in anything you'd like for t in either of these components, and you will get a defined value. Okay, so we don't have to worry about continuity. We know for sure that there's no breaks or gaps in our space curve that would affect how we construct our smooth intervals. And so all we are worried about is where this derivative might be equal to 0, or in other words, where the derivative vector would be the 0 vector. So the way that I like to go about checking that is to individually set the components equal to 0 and solve for t and see if they share the same value of t for when they equal 0. Okay, because remember, they have to be equal to 0 at the same time, at the same value of t. So let's take a look at that here. I'm going to set 2t equal to 0 and 3t squared equal to 0. And if we solve for t, we'll have t equals 0 here and t equals 0 here, right? Dividing both sides by 2 gives you t equals 0. And then dividing both sides by 3 gives you t squared equals 0. And you could take the square root of both sides and find that t equals 0. So what we find here is that the components of the derivative vector are both equal to 0 when t equals 0. They share the same value of t when they're equal to 0, which means at t equals 0, the derivative would be the 0 vector. So t equals 0 would be a point where this vector function has a node. The curve would come to a sharp point of some kind. So we would not include 0 in our open intervals for which the vector function is smooth. All right, but we can include all other values of t from negative infinity to positive infinity because there are no other domain restrictions on this vector function. So here's our final answer. Our smooth intervals will be from negative infinity to 0, not including 0, and then from 0 to positive infinity. Okay, those are the open intervals on which our curve is smooth. All right, and once again, that's because r prime of 0 would be equal to the 0 vector. And when that happens, that value of t is where the curve is not smooth, so we do not include that in our smooth intervals. Okay, and so just so you can see what this looks like visually, I'm not going to take the time to go through sketching this vector function. I've shown you how to sketch vector functions in a previous lesson, so I'm just going to give you the graph here. This is what our vector function looks like if you graph it. And as you can see, at t equals 0, we do have a sharp point. The curve comes into this sharp point and then comes out, but that point is the only location where the curve is not smooth. Everywhere else, you have a nice, smooth curve. Okay, that's it for this example. Let's take a look at another one. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful, then I'd invite you to join my membership site JK Math Plus, where you get access to many perks including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I will have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. For this example, we once again want to find the open intervals on which the curve represented by the vector function is smooth. And this time our vector function is r of t equals t minus 2 times sine t I plus 1 minus 2 cosine t j. And our domain is restricted here. We're just looking at values of t between negative 2 pi and positive 2 pi. Okay, so what we want to do here to determine where we have intervals of smoothness for this vector function is first of all, take its derivative. we want to find the derivative of this vector function and see where that derivative would be equal to the 0 vector. All right, so if we take the derivative here, we'll have r prime of t is equal to the derivative of the x component. The derivative of t is 1, and the derivative of sine is cosine. So we will have 1 minus 2 times cosine t times I, and then we'll take the derivative of the y component. The derivative of 1 is 0, and the derivative of cosine is negative sine, so we will just have positive 2 sine t times j. Okay, so now we want to know where this derivative vector equals the 0 vector, but before we do that, you do want to check for continuity. Are there any values of t for which either of these components would be undefined? And both of those functions are continuous. Both cosine t and sine t are continuous functions, so we don't have to worry about that. There are no values of t for which the derivative is undefined. And I don't think I wrote this last time, but you do probably want to make a note of this so that you know that you checked it, but I'll just write down continuity, check. Okay? So we don't have to worry about any points of discontinuity for our intervals of smoothness. But now, let's set both of these components equal to 0 and see if they are equal to 0 at the same values of t. All right, so we'll have 1 minus 2 times cosine t equals 0, and 2 sine t equals 0. Let's start with 1 minus 2 cosine t. If we add 2 cosine t to both sides of the equation, we'll have 1 equals 2 times cosine t, and then dividing both sides by 2 gives us 1/2 equals cosine t. All right, so what you want to ask yourself here is what values of t, or what values for cosine, gives you 1/2? And you want to remember the interval that we're working with here. We're looking at values of t between negative 2 pi and 2 pi. So there's going to be quite a few values of t for which cosine will be equal to 1/2. If you remember your special angles, you might at least come up with the first one here. From this equation, you should find that t equals pi divided by 3, but that is not the only value of t for which cosine equals 1/2. If you add pi to pi divided by 3, you'll get another value of t, which is 5 pi divided by 3. And those are the only two values of t in the positive direction on this interval, where cosine t equals 1/2. But there are some in the negative direction, right? We're not going from 0 to 2 pi. We're going from negative 2 pi to 2 pi. So what we can do is work with the negative versions of these values of t, and those would also be angles where cosine t equals 1/2. All right, so negative pi divided by 3 and negative 5 pi divided by 3 are also two values of t for which cosine t equals 1/2, which is where this x component would be equal to 0, right? Because if cosine t is 1/2, you have negative 2 times 1/2, which just becomes negative 1. So you have 1 minus 1, which is 0. So that component would be 0. All right, so these are the four values of t on this interval where the x component equals 0. But now what about the y component? Well, if we divide both sides by 2, you'll just have sine t equals 0. And then for what values of t is sine equal to 0? Well, this shouldn't be too hard. This is probably one of the angles that you have memorized for sine. We know that sine is equal to 0 at t equals 0, right? So sine of 0 is 0. But we also know that sine of pi is 0, and sine of 2 pi is 0. So we have pi and 2 pi. But don't forget that we also need to go in the negative direction to negative 2 pi. So we would also include negative pi and negative 2 pi. Those are the 5 angles on this interval for which sine of t would equal 0 and for which this y component would equal 0. All right, and so now we found all the values of t for which the x component equals 0 and the y component equals 0 for our derivative vector. And what you'll notice here is that none of them are the same, right? They don't share any values of t. The x component is equal to 0 at these 4 values of t, and the y component is equal to 0 at these 5 values of t, but none of them are the same. They're never equal to 0 at the same time. And so what we find here is nothing. We have found no points for which this derivative vector is the 0 vector. It just doesn't happen, at least not on this interval. And spoiler alert, it wouldn't happen for any interval for this vector function. Just because of the way it's set up, the two components will never be equal to 0 at the same time. Okay, and so our answer here is not really all that satisfying. We just did a whole lot of work for basically nothing, but we had to check it to see if we had any points where this curve had nodes, or where the curve is not smooth. And so here's my final answer. Our smooth interval is just the interval of the domain that we were given. But we're not going to include the endpoints because we are looking for open intervals for which the vector function is smooth, and it doesn't make sense to include the endpoints because technically those would be sharp points on the curve. And you'll see that when I show you the graph of the plane curve represented by this vector function. But first, let's just write down our smooth interval here. It would just be the interval from negative 2 pi to 2 pi. All right, that is the final answer to this example. All right, and so if you were to go ahead and graph this vector function, this is what you would find it looks like. It's got some looping action going on here. This is where t equals negative 2 pi, and then you head this way, make a loop, and come out to t equals 2 pi. And so clearly you can see that this plane curve is smooth everywhere on that interval, except at the endpoints, because those would be sharp points in a sense, all right? The curve just kind of ends at those two values of t, so it's not really smooth there, but everywhere else, the curve is smooth. Okay, so really, if our domain was not restricted, really this vector function would be smooth everywhere, but since we were given a restricted domain, we had to work with that domain when we set up our smooth interval. Okay, let's take a look at one more example for this video. All right, so here's our final example. We want to find the open intervals on which the curve represented by the vector function is smooth, and this time our vector function does represent a space curve. Our last two examples, we were working with plane curves, but this time we do have a vector function in 3D. It has three components. R of t is equal to t times I minus 3t times j plus tangent t times k. And so even though the vector function represents a space curve, the process remains the same. We're still going to take the derivative of this vector function, check to see if there are any points of discontinuity, and then check to see where all three of the components would equal 0 for that derivative vector. Okay, so let's take the derivative of our vector function here. We'll have r prime of t is equal to 1 times I minus 3 times j plus the derivative of tangent is secant squared. So we'll have secant squared t times k, right? For the other derivatives, I didn't really explain them because they're pretty simple. The derivative of t is 1, and the derivative of negative 3t is negative 3. All right, and so first things first, are there any values of t for which this vector is not continuous? And looking at the first two components, no, because they're just constant components, right? There's no values of t in the x or y components. The only component that might cause an issue is the z component, where we have secant squared t. And so if you're familiar with your secant function, you might remember that it's not defined at pi divided by 2 plus any multiples of pi. All right, it's just like the tangent function, which is also not defined at pi divided by 2 or any angle of pi divided by 2 plus a multiple of pi. Okay, so essentially what I'm saying here is that the secant function, and subsequently the secant squared function, is not defined at angles like pi divided by 2, 3 pi divided by 2, 5 pi divided by 2, or you could go in the other direction, negative pi divided by 2, negative 3 pi divided by 2. For any of those angles, in either direction, the secant function is not defined. And so those are going to be values of t for which our vector function is not smooth. All right, so we have to make a note of those values of t. And so here's what we learn. This component, secant squared t, is not defined for t equal to pi divided by 2 plus any multiple of pi. All right, so the way I'm going to represent that is n times pi, where n is an integer. Okay, basically all that means is n has to be a number like 1, 2, 3, 4, 5. It can't be 1.23 or 7.4, anything like that. It has to be a whole number. Okay, so we have to consider all of those values of t when we set up our smooth intervals for this vector function. But before we set up those intervals, we still haven't checked where this derivative vector function is equal to the zero vector. And so let's quickly do that. Remember that we want to set each of the components equal to 0 and see if they are equal to 0 at the same value of t. And you might have noticed that that's probably not going to happen because the first two components are constants, right? For the x component, we just have 1, and 1 is not equal to 0. And for the y component, we have negative 3, and negative 3 is not equal to 0. So the x and y components of our derivative vector are never equal to 0, so it's impossible for the entire vector to be the 0 vector. You will never have 3 components that are all 0. All right, so we really don't even need to check the z component. I still will because I want you to see all the work, but really you don't have to check this. But for the sake of completion, I'm going to write secant squared t equals 0, and let's try to solve for any values of t where this is equal to 0. If we take the square root of both sides, we have secant of t is equal to 0, and the secant function doesn't have any angles where it's equal to 0, right? There's no value of t that you could plug in here to get 0. It just doesn't happen. There are no solutions to that equation. All right, if it's been a while since you've seen the graph of secant, it looks something like this. You sort of have these parabolas that swap which side of the x-axis they're on. So it looks something like that. And you have these asymptotes at pi divided by 2 plus a multiple of pi. Okay, so that's what's going on here. None of these curves that are part of the graph of secant ever touch the x-axis. So as a result, secant never equals 0. Okay, so that's what's going on here. We have now determined that there are no values of t for which the vector function's derivative is equal to the 0 vector. So the only values of t that we have to consider when creating our smooth intervals for this vector function are these values of t for which secant squared t is not defined, because that makes the entire vector function's derivative not defined either. All right, so that's going to cause some issues with regards to smoothness. All right, so let's try to set them up here. I'm going to start by writing a specific set of intervals, but because these values of t kind of go on forever in both the positive and negative direction, we will have to write a generalized form of these smooth intervals. We can't write out any specific ones for specific values of t. We have to represent it with similar notation to what I wrote right here. All right, so as an example, we know that we're not going to be smooth at pi divided by 2 and negative pi divided by 2. But all the values of t in between there are going to be fine. So one example of a smooth interval would be from negative pi divided by 2 to pi divided by 2. That would be fine. Another example would then be from pi divided by 2 to 3 pi divided by 2. All right, you just don't include any of those angles where that z component would be undefined. All right, so these are some examples of specific smooth intervals, but how do we generalize that based on what we know about the values for which secant is undefined? Well, you'll notice that the two endpoints for these intervals are always an angle of pi apart, so all we have to do is let pi divided by 2 plus n pi be one endpoint, and then just make the other endpoint the same thing, but where the initial angle is smaller by an angle of pi. All right, so here's what I mean by that. I'm going to represent our smooth intervals like this. We'll have negative pi divided by 2 plus n pi, comma, pi divided by 2 plus n pi. All right, and that represents all the possible intervals that we could have where this vector function would be smooth. If n equals 0, then you just have the interval from negative pi divided by 2 to pi divided by 2. If n equals 1, then you're adding pi to both of those angles, so then you'd be looking at the interval from pi divided by 2 to 3 pi divided by 2. And you could continue to look at more and more intervals where this vector function would be smooth by picking more and more values of n to plug into this interval. Okay, and this works because the angle that we're adding n times pi to are both pi apart, which is always going to be true for your intervals of smoothness for this vector function based on what values of t its derivative is not defined. Okay, so I hope that makes sense. This is a little bit more complicated than the other examples in terms of setting up the smooth intervals because we had to generalize it. We couldn't write out specific intervals. We had to represent all the different possible intervals because our domain wasn't restricted for our values of t. Okay, and so to finish things off here, just like with the other two examples, I do want to show you the graph of this vector function so you can see visually the smooth intervals that we just found. So here's what it looks like. I drew a sketch ahead of time. What this vector function ends up being is basically a tangent curve that is contained within a plane, specifically a plane that cuts through the z-axis at this angle right here. The reason it looks like that is because if you were to go about sketching this vector function, eliminating the parameter in these two components, t and negative 3t, would give you a linear equation, and that linear equation would be a line that cuts through the origin, and so then that line would be extended along the z-axis to create a plane, and within that plane, the curve would be formed by the z component, which is the tangent function. So although this just looks like I'm drawing the tangent function in a 3D coordinate system, it's not quite like that. All these curves are actually contained within this plane that is at an angle cutting through the z-axis. Okay, but you can see that for this space curve, there are asymptotes which actually correspond to the values of t for which we found that the derivative was not defined. All right, so those would be our values like pi divided by 2, 3 pi divided by 2, negative pi divided by 2, and so on. All right, I'm just drawing a small section of the space curve here, but this would extend forever in both directions, and so you would have an infinite number of these curves and these asymptotes, and so you can see how there is an infinite number of these smooth intervals, which is why we had to generalize it. Okay, and you can clearly see that for those intervals, the curve is smooth. It's just not smooth at those asymptotes because the curve doesn't exist there. Okay, so I hope this was helpful in visualizing what we found here. But that is it for this example, and this was also the last example for this video. But if you do want to get some more practice finding smooth intervals for vector functions, feel free to check out my examples video for this topic that I'll have linked here on the screen. If you have any questions, please let me know in the comments, but if you don't have any questions, then this is all I had for now, so I will see you next time.